In section 1.2, we're going to work on the unit circle and understanding how it's created, what it's used for. So we want to be able to identify the unit circle and describe its relationship to real numbers. We're going to want to evaluate trigonometric functions using the unit circle. And we want to use domain and period to evaluate sine and cosine functions. And then we're going to use calculators to evaluate other trig functions. So what we have down below here is the unit circle. And remember when we talked about radian measure, radians, right? Just to remember, a radian was the measurement of an angle that creates the arc of a circle that's equal to the radius. So 1 radian is the measure of an angle that creates an arc length whose length is equal to the radius. So they're inherently tied to the discussion of circles. And when we say the unit circle, it's called the unit circle because it has a radius of 1 unit, which makes it very easy to plot because we go right and left 1, we go up and down 1, and then we're able to make this circle. And we know that our the length of our arc, the dimension of our arc will be the size of the radius times the measurement of theta in radians. So if theta is 1 radians and the radius is 1, then we know that the arc length will also be 1, the same as the radius. Hopefully that all makes sense to you guys. Okay, when we start talking about working with the radius, or the unit circle, when we have an angle in standard position, like this angle theta here, its initial side is here on the x-axis and it terminates at this point t. And if we wanted to look at the distance for t, finding this measurement, right, there are different ways that we might go about it, but for now, you can see that if I take my arc length and I stretch it up to make it vertical, that's what would happen with this. Okay, and that would again be the length of the arc when we deal with arc length is equal to the radius times theta in radians. But also from this point here, we can calculate a number of different trig functions. So we know that for this angle, the sine of the angle would be equal to the y-coordinate, the cosine would be equal to the x-coordinate, and tangent would be y over x. And then of course cosecant is the inverse of sine, secant is the inverse of cosine, and cotangent is the inverse of tangent. And the reason this works is that if I were to take and drop a line here straight down, I will have created a right triangle. Okay, so this makes this a right triangle. And when we look at the vertical change here is the y-coordinate, that's y, and horizontal change is x, and we know that the radius of our circle is 1, so our hypotenuse is 1. So when you're looking at sine is equal to opposite over hypotenuse, y over 1 is just y. And cosine is adjacent over hypotenuse, so x over 1 just becomes x. And then tangent is equal to sine divided by cosine, so we have y over x. That's why it all works. So the unit circle then is very helpful to us in terms of trying to calculate the basic trig functions without whipping out a lot of technology. So again, this is the same graphic I had on the previous screen. You could also say that tangent is equal to sine of t over cosine of t, and that would be y over x. So the fact that the unit circle is built off a circle with a radius of 1 is what allows all of this to be so simple as just pulling a coordinate. Otherwise, I'd have to use the Pythagorean theorem to find that hypotenuse. So as we start working with the unit circle, this is the unit circle split into two different parts. So you see here we have measurements that are multiples of 30 degrees, or pi over 6. So 30 degrees is 1/3 of 90 degrees, and pi over 6 is 1/3 of pi over 2. So up here, you know, this is 90 degrees, and in radians, that measurement is pi over 2. And so these are all the multiples of 30 degrees. So it's 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, and 330, and 360. They're all here. Whereas these are multiples of 45, 45 degrees, or pi over 4, right, if we're talking about radians. And what you'll find is it's very easy to build the unit circle because all of these different coordinates, they repeat. So here I have a half, and on the next one, the half, here it was the y, there it becomes the x. Over here, it's still the x, but now it's negative, and then it's back to being the y. And now it's the y again, but it's negative, and it's the same x that I had above it. But you'll notice that they're all tied to 1/2. And when you look at the other coordinate, you'll see that it's always radical 3 over 2. Positive and negative, yes. Sometimes it's the x and sometimes it's the y. But it makes it very easy because these are all the same, right? So when you look over at the multiples of 45, it's even easier. All of them are the square root of 2 over 2. And they just change to be positive or negative based on what quadrant they're in. Okay, so it's very consistent and it's very predictable. So if I want to do the 6 trig functions for these different points, I'm going to look for negative 5 pi over 6. So I'm going to do this one first because this one's kind of a special case and this one's kind of a special case. I'm going to start with this one. It's a little more logical. So if I follow my angle, there's 1, 2, 3, 4, 5 pi over 6. This is where the terminal side is. I know that my sine is equal to the y-coordinate, and the y-coordinate here is negative 1/2. And I know that cosine is the x-coordinate. That's negative radical 3 over 2. And I know that tangent is going to be 1 divided by the other, right? Y divided by x. So if I have negative 1/2 divided by negative radical 3 over 2, I would invert this and multiply, right? And the 2's will cancel. I'll get a positive number. I'll get 1 over radical 3. And then when I simplify this, this is going to become radical 3 over 3, and this is my tangent. Okay, if we talk about cosecant, it will be the inverse of this, so it will be negative 2. If I talk about secant, it's the inverse of this, so I'm going to invert it. But then I'll have a radical in the denominator, which I can't have. This will simplify to be negative 2 root 3 over 3. And when I invert this one, it's just going to be radical 3 over 1, which would be radical 3 for cotangent. So there's cotangent, here's secant, here's cosecant. I really didn't leave enough room on this slide to write this all out. My apologies. Okay, so let's make a little more room. When I'm talking about negative 3 pi over 4, negative 3/4 pi, that would be over here. So there's 1/4, 2/4, 3/4 pi. This is negative 3 pi over 4. This one was negative 5 pi over 6. And I'm going to go through this all again. So I know that sine is the y-coordinate. It's negative radical 2 over 2. Cosine is the x-coordinate. It's the same, negative radical 2 over 2. Tangent then is going to be this divided by that. They're both the same, so that's 1. Cosecant is going to be the inverse of this, 2 over radical 2. And when I rationalize the denominator, I'll get negative 2 radical 2 over 2, which will simplify to just be the opposite of radical 2. And that would be the same for this one, for secant. And the inverse of 1 is 1. So cotangent will also equal 1. Now when you look at pi over 2, that's this point up here, and this is a little more unique. So if you talk about sine is equal to 1, cosine is equal to 0, and tangent is equal to y divided by x, but I can't divide by 0. It's undefined. And then cosecant would be the inverse of 1, which is 1. Secant would be the inverse of 0, which is undefined. And cotangent would be undefined. So it's a sort of special case when you're dealing with the poles here. When you've got 0 involved, it becomes complicated. And with t is equal to 0, then we have sine is equal to 0, and that means cosecant is undefined. I have cosine is equal to 1, which means that secant is equal to 1. And when I have tangent is equal to x over y, that's 0, and cotangent would be undefined. And I made a mistake actually up here. Cotangent would not be a problem. It would be x over y. So I made a mistake up here actually on tangent, which should be. So I made a mistake up here with cotangent. It would actually be 0 over 1, which would be 0. My mistake. Alrighty, so that's just using the unit circle really quickly to evaluate these guys. It's a lot of data on one slide. I should have probably split this up and put more slides in. I apologize. And when we start talking about domain and period, right? So let's start talking about domain and range. So when you look at the domain of all the x values, you'll see that they go from -1 to 1. So this would be our domain. And our range are the limits of our y values, and you see that they also go between -1 and 1. And when you start thinking about the period, right, the period is the length around our unit circle, which in this case is 2 pi. That's the period, right? So we're working between, our theta value is between 0 and 2 pi. That's the period that we're working with. So when we find the value for, or we want to find the value for an angle, for say sine, there are an infinite number of angles that have a particular sine value. And every time I go around the circle, the whole period one more time, which in this case is 2 pi, I'm going to arrive back to the same terminal side, and consequently, I will have the exact same trig values for all of those angles. And that's what this is showing, is that this is basically a way to write all of the coterminal angles to t. They're all going to have the same sine values, and they're also all going to have the same cosine values. So angles that are coterminal share the trig functions. They're all the same. And this is the way you would write it if you want to start talking about repeating on through toward infinity. If we start talking about what a periodic function is, so a periodic function is a function that repeats over a period. And a function f is periodic when there exists a positive real number c such that the function of t plus c equals the function of t. And if you go back, that's what we're talking about here. The function of an angle is equal to the full trip around the circle times the number of times you go around the circle. And so 2 pi becomes a significant part of the period dealing with the unit circle. In other functions, it might be a different value. Okay, so the smallest number of c, which is this value here, this value becomes, the smallest number of c is called the period of the function. And what that period is, it's the point where it repeats. So if you think about we haven't done this yet, but we're going to. When you talk about a sine function, it does this, and then it does it again, and then it does it again. And so this distance, this is called the period. So if we want to use the period of a cosine function to evaluate the cosine of 9 pi over 2. Okay, so let's look at 9 pi over 2 and figure out where does it belong. Okay, so 9 pi over 2, right? If I go around the whole circle, that's 4 pi over 2. That's 2 pi. And I go around, right? Once around, 4 pi over 2. Twice around, 8 pi over 2. And one more pi over 2. This is 9 pi over 2. So this is pi over 2, and it's also 9 pi over 2. They're coterminal. So if I want to think of cosine, I'm looking at my x-coordinate, right? This is at 0, 1. The cosine of 9 pi over 2 is equal to 0. Okay, if I want to do the same with 7 pi over 3, negative. So this would be 3 pi over 3, 6 pi over 3, and 7 pi over 3. And this is negative pi over 3. Well, pi over 3 has an x-coordinate that is radical 3 over 2 and a y-coordinate that's negative 1/2. That's this point on the unit circle. So if I want to find sine, it would be negative 1/2. And if we want to evaluate cosine, given that cosine of negative t, evaluate cosine of the opposite of t is 0.3, what's the cosine of t? So when we talk about cosine is related to x. So if we think about things like here's pi over 3 and here's negative pi over 3, right? So if cosine is related to the x-coordinates, you notice the x-coordinates, they don't change. So cosine of t would be equal to the same value, 0.3. Okay, now if we want to use a calculator to evaluate these guys, if I want to do 5 pi divided by 7, I can go ahead and do, let's see, 5 times pi equals, and then I can divide it by 7 equals, and then I can find the sine. 0.04 essentially. So when we talk about that, then A, it's 0.04, and B, a little more possibly confusing, cosecant. Remember, cosecant is the inverse of sine. So let's find, I have 2.0, and then let's find its sine value, and then I'm going to find the inverse of that. Oops, sorry. So it's 28.65. All right, and now what we should have done is explain the unit circle and its relationship to real numbers. We wanted to state unit circle definitions of the trig functions. We evaluated trig functions using the unit circle. We talked about domain and period to talk about sine and cosine functions. And we went through using a calculator to evaluate trig functions. All right, that's it for section 1.2.